This video is about how I use the mathematics from my engineering degree to describe any type of polygon that I want. Like this 12-sided figure on the left, an irregular dodecagon, which I drew by mapping 12 complex numbers in the complex plane. This shape has been constructed from these regular polygons on the right, and by tuning the sizes and angle of these shapes, I can use them to construct any 12-sided shape that I want. I can also transform this object into a hexagon, then a square, then a triangle, then a star polygon, and finally a line, and then the same shapes repeat but with the points A through L in the opposite rotational order. What you're seeing is not just geometry, but also a representation of math that has been used throughout electrical engineering and computer science for many applications. In this video, I will untangle the math here to show you how to construct any polygon that you want. What does an electrical engineer in 1918, a mathematician in 1940, two computer scientists in 1965, and the founder of Pixar in 1998 all have in common? All of them wrote papers in those years that contained some version of the same equation, the discrete Fourier transform. In 1965, James Cooley and John Tukey referenced this equation directly in applications to signal processing, such as for frequency analysis of electromagnetic waves. In 1998, Alvy Ray Smith, the founder of Pixar, writes this equation for deconstructing polygons in computer graphics, such as the decomposition of this irregular triangle into two regular triangles. He references a theorem by Bernard Neumann, a mathematician, which is about the same topic. Neumann references his own father's textbook about the topic of symmetrical components in his paper, which was created by Charles Fortescue for solving problems in unbalanced power systems. In electrical engineering, this equation is used to map three-phase unbalanced vectors into three sets of balanced vectors for solving problems in power system unbalance. So this idea has been introduced by many people for many applications, and in its fully expanded form, the equation represents an input set of complex numbers multiplied by a matrix made up of powers of roots of unity, which outputs a new set of complex numbers. This video will focus on the geometric aspects of this equation. I will show the symmetrical components perspective which I was originally trained on, and which provides a good algebraic view, and the one described by Neumann, which would come to be known as the Peter Douglas-Neumann or PDN theorem, which uses more geometric methods. For the first example, I'll use three input points of complex numbers z, p, and n, which I will refer to as components. The naming of these components will be explained in a minute. Multiplying z down the left column of the matrix outputs 3 points in the complex plane that are all equal to z. Multiplying p down the middle column produces 3 points that form an equilateral triangle in the complex plane. Consider all green points associated with A, all red points associated with B, and all blue points associated with C. Then tracing a triangle from A to B to C on the P chart draws a triangle in a clockwise manner, and I will arbitrarily refer to this as a positive rotation for the naming of the P component. Multiplying n down the right column of the matrix produces 3 points that form an equilateral triangle which traces in a counterclockwise way. So n is associated with negative rotation. Z represents a set with zero rotation because the ABC points have no rotational order on the Z chart. Multiplying the complex values z, p, and n by the matrix generates symmetrical objects which sum together to form an asymmetrical three-sided triangle. Here I'm showing the sequence of the full vector summation. Now the PDN theorem gives us a completely different construction of this. First, the z component just represents simple translation of the shape across the plane, but the value of z doesn't affect the shape at all. To extract the positive component, external equilateral triangles are erected from the irregular shape. The vectors that point from the irregular triangle center to the external triangle centers maps directly to the p vectors after a 180-degree rotation. Here's a sweep of P around the complex plane to see its effect on the final triangle. Repeating the same process for internally erected triangles, the result maps to the n vectors, and changing its shape replays all the variations of the ABC triangle as rotating P did. Now there are a couple of equations that you can pull from Bernard Neumann's paper that give a metric for how unbalanced the triangle is. On the charts, I've labeled the side lengths of the triangles with lowercase letters to use as reference values for these equations. The first is the statement that the area of ABC is the difference of the areas of the two equilateral triangles. This is illustrated in a literal way by showing the area of the ABC triangle here being equal to the difference of the areas of the P and N triangles. The equation is represented algebraically this way. The PDN theorem also states that the sum of the squared sides of a polygon is the sum of the similar sums formed for its symmetrical components. This statement is illustrated in a literal way by erecting squares from the sides of all of these triangles and fitting them into this equation. This is represented algebraically this way. If the magnitude of P and N are unknown, they can be solved for by combining both of these equations. Taking the ratio of N over P provides a measure of how unbalanced or non-equilateral the triangle is. Now there happens to be an amazing approximation for this complicated formula that is used in my field of power engineering. First you take the average of the sides of the A, B, and C triangle, then look at which triangle side deviates the most from the average, and divide that difference by the average. This value is typically referred to as imbalance. For a given value of N over P, say 0.05 in this example, the value of imbalance stays very close to 0.05 as the mutual angle of N to P is varied by 360 degrees. For the remainder of this video, I'll review the decomposition of polygons using the matrix form instead of the totally geometric construction from the PDN theorem, since that geometric construction gets very messy for larger polygons. Before going on to decompose polygons with 4 and more sides, I want to briefly review the 2x2 matrix example since it introduces a symmetrical component that's unique for even-numbered matrices. First, it contains the z component again, which appears in the decomposition of all polygons and always represents translational symmetry of the object. The second component I call S because it splits the values to land on opposite sides of the origin of the complex plane. Here's an animation of the vector construction of this object. In the case of 4 points, there is a 0 component again, a positive rotation component oriented A, B, C, D clockwise, a split sequence because 4 is an even number, and a negative rotation component ordered A, B, C, D counterclockwise. The positive and negative components create variations of parallelograms, and adding in the S component splits the points like before and turns the parallelogram into a completely arbitrary 4-sided polygon. I'll play through some more constructions of this figure before moving on to 5-sided polygons. In the case of a 5-pointed figure, there is no split component because 5 is not even, but there are 2 positive and 2 negative components. In this second pair of positive and negative components, the step from A to B, B to C, and so on is 144 degrees instead of 72 degrees, which traces out a star polygon, not a pentagon. With these transformations, skewed pentagons and pentagrams can be created, or combined to create totally arbitrary 5-sided shapes. Now the 6-point example, and this will be the last one I'm decomposing before jumping back to the 12-sided example from the beginning of the video. Since 6 is even, there is the S component again, and there are 2 sets of positive and negative components. The P2 and N2 components have 120 degree steps going from A to B and so form equilateral triangles. So with this transformation, all 6-sided and all 3-sided polygons can be created. As we'll see in a minute, when the number of input points to the equation is a composite number, then that number's divisors are associated with other regular polygon shapes. In this case, since 6 is divisible by 3, the points overlap and we get a triangle. So with all of that now behind us, let's jump back into the dodecagon example. I picked 12 because it is a highly composite number and can be divided by 2, 3, 4, and 6. Just like before when divisibility by 2 created a split sequence and divisibility by 3 created triangle-like sequences. The many ways to divide 12 allows you to construct a line, a triangle, a square, or a hexagon out of the 12 points. Since 5 is the only number missing from this divisibility, the 5th component produces an ordering of vertices that do not overlap, creating the star pattern shown here. Now I said in the beginning of this video that symmetrical components allows you to create any polygon that you want, and I've made free tools on Geogebra that you can try this out on that are linked in the description. There is one last proof from the PDN theorem that helps here, which is that the shapes associated with the positive and negative sequences provide positive and negative areas, respectively, to the final shape. Since the Z and S components have no area, adding them in doesn't change the area of the shape, even if the shape itself may change. That's all I have to say about symmetrical components for now. I hope you enjoyed the video. Please like and subscribe.